Am I audible? Good evening, everyone. Welcome to Goscore Learning, the fastest growing edtech company in Middle East with an aim to provide quality education for all. I am your Dhanya ma'am. Today I am here with the third part of your electrochemistry chapter. In the previous video, we have discussed about the electrode potential, electrochemical series, and Nernst equation and all. Today, we are going to discuss about the Faraday's law and about the Kohlrausch's law and some numericals based on that also. So, can we start the session? First, we can discuss about the Faraday's law. That is the quantitative aspects of electrolysis and Faraday's law. There is two laws you have to learn. That is, first one is the Faraday's first law and second law. First, we can see what is the Faraday's first law of electrolysis. According to the first law of electrolysis, the amount of the chemical reaction, that means the mass of the substance that is either deposited or liberated at the electrode, is directly proportional to the quantity of electricity passed through the electrolyte. We know that only the melted or the aqueous solutions will contain the electricity. That is what we called electrolyte, right? So, according to Faraday's first law of electrolysis, the amount of substance that is either deposited or liberated at the electrode will be directly proportional to the quantity, how much electricity we have passed through the electrolyte solution. Okay, so imagine if W amount of substance is either liberated or deposited at the electrode. Okay, just a moment. If W amount of substance is deposited or liberated at the electrode, according to Faraday's first law, this amount is directly proportional to the charge or the quantity or the amount of electricity that we have passed through that particular electrolytic solution. Okay, so here when I change this proportionality, I can write it as W is equal to Z into Q. Then what is the Z? The Z is nothing but the electrochemical equivalent. Okay, the Z is the electrochemical equivalent. Okay, so what we got? It is W, the amount of substance deposited, is equal to Z into Q. So if we are passing I ampere of current, we are taking I ampere of current and we are passing this current for T second. What is the value of this Q? Charge is equal to the current into time, right? Q is equal to IT. If I am applying this to this equation, what I can write? W is equal to Z into I into T, where W is the amount of substance, Z is the electrochemical equivalent, I is the current passed in ampere, T is the time in second. Okay, now let's see this I value. If I am passing 1 ampere current, okay, I is equal to 1 ampere. And if T is equal to 1 second, what I will get? W is equal to, if these two are 1, what I will get? W is equal to Z, right? So, I can define this electrochemical equivalent as the amount of substance deposited where 1 ampere of current is passed for 1 second. Isn't it? This electrochemical equivalent is the amount of substance, the W, the amount of substance deposited when 1 ampere of current is passed for 1 second time. Right? So that's about the Faraday's first law of electrolysis, that is the amount of substance deposited or liberated at the electrode is directly proportional to the quantity of electricity passed through that particular electrolytic solution. Okay, that's about the first law. Now let's see what is the Faraday's second law of electrolysis. So here, for explaining the Faraday's second law, let's imagine we have taken one beaker containing silver nitrate solution. Okay, we have taken the silver nitrate AgNO3 silver nitrate solution. To this I have put one cathode and one anode. Okay, I have connected one anode and cathode. Here I am taking another electrolytic solution, that is copper sulfate. We can take copper sulfate. Okay, so this is copper sulfate solution. In that also I am dipping one plus cathode and okay, connecting these two electrolytic solutions in a series way. Okay, see, I'm connecting this from to the battery to this and this to this. Okay, now see, here I have connected two different electrolytic solutions in a series. Right, now see the definition for the second law. When the same quantity of electricity is passed through the solutions of different electrolytes connected in series, the mass of substance produced at electrode is directly proportional to their equivalent weight. So here we have taken two different electrolytes and we have connected it in series, and if you are passing the same amount of electricity through these solutions, according to Faraday's second law, the mass of substance deposited at electrode will be equal to their equivalent weight. See here, silver nitrate and copper sulfate, right? So according to Faraday's law, the amount of silver Ag deposited will be equal to equivalent weight of Ag. Right? Same way what I can write, the amount of copper deposited. The amount of copper deposited at electrode will be equivalent weight of copper. Right? Here we have taken two different electrolytic solutions and have connected it in a series. And if you are passing the same amount of current through those electrolytes, according to Faraday's second law of electrolysis, the amount of substance deposited or the mass of substance produced at the electrode is directly proportional to their equivalent weight. Okay, so if you are taking the silver nitrate solution and copper sulfate solution, the two different electrolytes, and you are connecting these two electrolytes in a series, the amount of copper deposited will be directly proportional to the equivalent weight of copper, and the amount of silver deposited will be directly proportional to the equivalent weight of silver. That is what the Faraday's second law of electrolysis. So I hope the first law and second law is clear for you, right? Now let's see some quantitative aspects of electrolysis. If you are taking a molten sodium chloride, it will be dissociating into Na plus and Cl minus ions, right? See, for Na plus ion, what Na plus ion will be accepting one electron and changing to sodium, right? So what I can say, one electron will involve is been involved to produce one sodium, right? There is one mole of electron. What it will be? 1 mole means 1 mole is nothing but the Avogadro number of particles, right? So if it is 1 mole of electron, it will be 1 mole of sodium, isn't it? Same way we can write for chlorine also. Cl minus. Okay, the Cl minus will give half Cl2 plus 1 electron, right? So what we can write, 2Cl minus will be giving Cl2 plus 2 electron. Here what we can see, 2 electrons are required to produce 2 chloride ions, right? Same way, 2 moles of electrons will be required to produce 1 mole of chlorine, right? So here, see, what is the charge of the electron? We know the charge of electron is, charge of one electron is 1.602 into 10 the power minus 19 coulomb, right? 1.6021 into 10 the power minus 19 coulomb. What will be the charge of 1 mole of electron? Charge of 1 mole of electron? 1 mole of electron means, 1 mole means nothing but the Avogadro number. So you have to multiply this number with the Avogadro number, right? So that is 1.602 into 10 the power minus 19 into, what is the Avogadro number? 6.022 into 10 the power 23. So when you multiply this, you will be getting a value approximately equal to 96,500 coulomb per mole, right? And this quantity of electricity is what we call the Faraday. What it is called? A Faraday. Okay. So 1F means this quantity of electricity or the quantity amount of charge passed when 1 mole of electron is used is called the 1 Faraday, and its value is approximately equal to 96,500 coulomb per mole. Okay. So here see how many electrons are involved. 2 electrons. So it will be 2 Faradays required there, right? So that's about the quantitative aspects of electrolysis. Okay. Now let's see some very important points that you should know about the Faraday's first law, second law and quantitative aspects. That is for calculating the amount of either liberated or deposited by certain quantity of electricity. If you want to find out the amount of substance, the first thing you have to do is write a balanced chemical equation. Write the balanced electrode equation and number of electrons given and the number of electrons. Then give the number of Faraday required for the number of moles of that substance in the balanced equation. Okay. So for finding out the amount of substance, you have to first find out how many electrons are involved. Based on that, you can calculate how much Faraday required, how much charge required for the reaction, right? And the second one important reaction as the equation is the quantity of electricity in coulomb. Okay. So quantity of electricity in coulomb, Q is equal to I into T. That is current into time. Okay. And I already told you that the 1 Faraday always liberates 1 gram equivalent of the substance. And the electrochemical equivalent Z is equal to weight deposited by 1 coulomb. That is the equivalent weight divided by 96,500. Okay. So these are the main points that you should keep in mind. Now let's see one numerical based on this. How many coulombs of electricity are required for the complete oxidation of 90 gram of water? Okay. So first we can write the balanced equation. Okay. H2O dissociate to give 2H plus half O2, right? So here O2, 2 minus. Okay. So here it's clear from the equation that there 2 electrons are involved, right? So for what we can write as here 2 electrons are involved. That means how much charge it required? How much charge it required? 2 Faraday, right? So we know that 1 mole of water, it is 90. Or either you can do it like this. Here we have given the mass 90, right? What is the molar mass of water? It is 80, right? So what will be the number of moles? Number of moles is equal to given mass by molar mass. You will get it as value 5, right? So here from this balanced equation, it is clear that for 1 mole of water, how much charge you require? You require 2 Faraday charge, right? So here 90 gram water means it is 5 moles, isn't it? So for 5 moles of water, it's nothing but 2 into 5 into Faradays. That means 10 into 96,500. That is 965,000. This much coulombs of charge is required. This much coulombs of electricity are required for the complete oxidation of 90 grams of H2O. Right? Either you can do like this because 1 mole of water means it is 18 gram, right? 18 gram require 2 Faradays of electricity, right? Then you can check for 90 gram, right? That it will be 2 into 96,500 divided by 18 into 9. Okay, here also when you cut it, it will be 5. 5 into 2, you will get same answer. You can do it in any way. If you get the concept clear, you can do it in your logical way. Okay. Now let's see the next question. Two electrolytic cells containing silver nitrate solution. So one of the electrolytic cell is silver nitrate solution and the copper sulfate solution are connected in series. Okay. Steady current of 2.5 ampere. So current is 2.5 ampere current was passed through them till 1.078 gram of silver were deposited. Then you have to find out how long did the current flow, what weight of copper will be deposited. So we have connected two electrolytic solutions, that is the silver nitrate and the copper sulfate, and you are passing the same amount of current, that is 2.5 ampere current through these two solutions, and after certain time, after a particular time, 1.078 gram of silver was deposited. You have to find out what is that time period, and during that time period what will be the amount of copper deposited. So how we will solve this? Okay, here I is given. So we can find out the time by Q is equal to I into E, right? So we want to find out the time and only the current value is given. Okay, current in ampere is given. So first you have to find out the charge required, right? So for that, what you have to write first the equation. Okay, so for silver nitrate, AgNO3 giving Ag plus NO3 minus, right? So here only one electron is involved, right? So what we can write? Only 1 mole of electron, or simply we can write for 1 mole of silver, 1 mole of Ag require how much charge? 1 electron means 1 Faraday, right? It require 1 Faraday charge, right? Here we have taken the 107.8 gram, right? So for 107.8 gram of Ag require how much? Sorry. Okay. Before that, just check. So 1 mole of Ag require 1 Faraday current, right? See, here we have a deposit of 1.078 gram of Ag. How much required? That is what we want to find out, right? So 1 mole of Ag means it is It's given in the question as 1.78 gram of Ag will be deposited by 1 Faraday. That is 96,500, right? So, you can easily calculate how much charge is required for 1.078, right? For 1.078 this much gram, what will be for 1.078 gram of Ag? It will be equal to 96,500 divided by 107.8 into 1.078, right? That is 96,500 divided by 107.8 into, I can rewrite this as 107.8 into 10 the power minus 2. These are same, right? 1.078, I can rewrite it as 107.8 into 10 the power minus 2. So these two terms will be cancelled. And what I will get in the final? 96,500 into 10 the power minus 2. That is equal to 965 coulomb. Okay. This much of charge is required for the deposition of 1.078 gram of silver. So you got the Q value, you have your I value here. You can easily find out the time required, right? Time T is equal to Q by I. That is equal to Q is 965 divided by I value is 2.5. Okay. You can do the calculation and your value you got will be 386 seconds. Okay. So when you divide this 965 divided by 2.5, you will get the value as 386 second. Now you got the time required, right? So next question, what is the sub question related to this? What weight of copper will be deposited? So for that, you have to write the, wait. For that, you have to first write the equation for copper. You're taking the copper sulfate solution, right? Then it will be Cu2 plus SO4 2 minus. So he see how many electrons are involved here? 2 electrons, right? So for depositing 1 mole of copper, how much charge required? It will be 2 Faraday, right? So here, see. So here, what you want to find out? If the atomic mass of copper is 63.5, when you're passing the same current 2.5 ampere for 386 seconds, what will be, how much copper will be deposited? Okay, so what we can write, 63.5 copper require 2 into 96,500, right? But here we are getting only how much charge? We have only 965 charge, right? So for 965 coulomb, how much it will be? 63.5 divided by 2 into 96,500 into 965, right? Because from this much 2 Faraday, it will produce 63.5 gram of copper, right? That's what we get from the equation. From the 2 Faraday coulomb, if you are applying, then you will get 63.5 gram of copper. But here what we find out, we are using only 965 coulomb, right? So find out how much copper will be deposited if you are passing 965 coulomb of charge. Then this will be, right? 31.7 divided by 100. So you will get 10 the power minus 2. That is 0.317 gram of copper will be deposited when you are passing 965 coulomb of charge. Okay. This is how we can solve this equation, that is You have to find out the time. For that, initially you have to find how much charge is using. So that is what we are finding out here, 965 coulomb. Once you get this, simply by substituting in the equation, you can find out the time required. And for finding out the amount of copper deposited, write the equation first and find out how many electrons are involved. And here we are taking only 965 coulombs of charge, electricity. So based on that, from the 2 Faraday, you are getting this much, 63.5. That's the equivalent weight. Then if you are using only this much of current, how much product or how much copper will be deposited? That's what we got as the value, 0.317 gram. Okay, so I hope it is clear for you. Now, we can see the conductance of electrolytic solutions. Here we are learning some few words which you are already familiar with, right? I think in physics also you are familiar with all these terms. So first we can see the resistance and resistivity. What is resistance? Usually the resistance we are representing with the letter R. Okay. And resistance is the hindrance caused to the flow of charge. Okay, the resistance, hindrance caused to the flow of charge, which is represented by the letter R. Okay, and we clearly know that the resistance is directly proportional to length and inversely proportional to area. So if you are taking an electrolyte of length, one electrolyte, the distance between the electrolyte is L length and the area is A, we can say that resistance is directly proportional to length and inversely proportional to area. So if I am changing this proportionality, I can write it as R is equal to rho. This is what the proportionality constant. Okay, in L by A. Here, this rho is what called, rho is nothing but the resistivity. Rho is nothing but the resistivity. Okay. So, what will be the rho value? Resistivity is equal to resistance into area divided by length. Simple. Okay. So, resistance is the hindrance caused to the flow of charge and is directly proportional to the length and inversely proportional to area. So, you can write it as R proportional to L by A. When you change the proportionality into equality, you will get R is equal to rho into L by A, where rho is the proportionality constant and this proportionality constant is nothing but resistivity. And you will clearly know that what is the unit of this resistance? The unit of resistance is ohm, or we can represent it like this, right? Then what will be the unit of resistivity? Resistance unit is ohm, right? What is area? If you're taking in area in centimeter, it will be centimeter square divided by length. It is centimeter, right? So, the centimeter cancelled. So, what will be your answer? It will be, the unit of resistivity will be ohm centimeter, right? That's about the resistance and the resistivity. Okay, we are representing the resistance with the letter R and the resistivity rho. Okay, now the next term is the conductance and the specific conductivity. Conductance is nothing but the reciprocal. Simply the reciprocal of resistance. Okay, so resistance is R, right? So conductance is nothing but the reciprocal of resistance. Okay, and we are representing this conductance with the letter G. Okay, so we can say the conductance G is equal to 1 by R. Okay, you know the value of R, right? 1 by rho L by A, that's equal to 1 by rho into A by L. That's what the conductance. And about the specific conductivity, we will use the term conductivity or specific conductivity. Both are okay. Okay. This conductivity is usually denoted by the letter kappa. Okay. The conductivity is nothing but the reciprocal of resistivity. Okay, it's the reciprocal of resistivity. Okay, so what we can write, resistivity, what we got here, resistivity is equal to R A by L, right? So I can write it as 1 by R into L by A, right? So 1 by R into L by A. What is this 1 by R? It is the conductance, right? So I can write conductance into this L by A is called the cell constant. So I can simply write the conductivity is equal to, conductivity is the conductance into cell constant. That means the kappa is equal to 1 by R. That is what the G, right? The 1 by R, the conductance G into L by A. Kappa is equal to G into L by A. Okay, this is the relationship between the specific contact resistance, resistivity, conductance and specific conductivity or simply the conductivity. Okay. Now, see, we want to learn two more terms, that is the equivalent conductivity and molar conductivity. Okay. So, see, equivalent conductivity is, the equivalent conductivity means equivalent conductivity of a solution which we have V volume, we have diluted it to V volume, is defined as the conductance of all the ions. When you are diluting the electrolyte, definitely there will be ions producing, right? The equivalent conductivity is defined as the conductance of all the ions produced from 1 gram equivalent of electrolyte. Okay. It is the conductance of all the ions produced from 1 gram equivalent of electrolyte. We are dissolving in V centimeter cube of the solution where when the distance between the electrode is kept 1 centimeter apart and the area of electrode will be so large that the solution is contained within it. Okay. So, equivalent conductance is the conductance of all the ions produced when you dilute the 1 gram equivalent of the electrolyte. And usually this equivalent conductivity we are representing with a lambda equivalent. Okay, lambda equivalent, and this equivalent conductivity lambda equivalent will be equal to the specific conductivity into specific conductivity into V. Okay, the volume V. Okay, so I can rewrite it as specific conductivity is nothing but the kappa, right, into 1000 divided by normality. This is what the equation for equivalent conductivity, that is lambda equivalent. Okay, same way here we have mentioned the conductance of all ions produced from 1 gram equivalent, right? Instead of this 1 gram, if you are taking 1 mole of substance, okay, instead of this 1 gram equivalent of electrolyte, if you are considering the 1 mole of electrolyte, then the equivalent conductivity is renamed as molar conductivity, which we represented with lambda m. Lambda m is nothing but the molar conductivity. Lambda equivalent is nothing but the equivalent conductivity, that is the conductance of all ions produced from 1 gram equivalent of electrolyte, and the lambda m is the molar conductivity, that is the conductance of ions produced by 1 mole of electrolyte. The rest all are same. Okay. So here lambda m will be equal to specific conductivity into 1000 divided by, instead of normality, since we are considering for 1 mole of the substance, it will be molarity, right? So these two equations you should be familiar with. Okay. So this is the equivalent conductivity. This is the molar conductivity. Okay. So I hope this equivalent conductivity and molar conductivity is clear for you. Now let's see one numerical, simple numerical based on the resistance and conductivity and all. See, the electrochemical resistance of a column of 0.05 molar NaOH solution of diameter 1 centimeter and length 50 centimeter is 5.55 into 10 to the power 3 ohm. Calculate the resistivity, conductivity and molar conductivity. Okay, see what are given here. The molarity of the solution. The molarity of the solution is given as molarity equal to 0.05 molar, right? And the diameter. The diameter is given as is equal to 1 centimeter. Length is given as length is equal to 50 centimeter. And the resistance, the electrical resistance, okay, the electrical resistance is given as resistance is equal to 5.55 into 10 raised to 3 ohm, right? We want to find out the resistivity. What is resistivity? Resistivity is equal to rho is equal to R A by L, right? Isn't it? Resistivity equal to R A by L. For that, resistance is provided, length is provided. The area is not given directly, but it is the diameter is given since it's a column of solution. The diameter is given in the question. So, you can find out the area as area is equal to pi r square, right? So, 3.14 into here the question it is given the diameter. So what will be the radius? 1 by 2, right? The diameter is 1 meter, then the radius will be 1 by 2. Okay, you have to find out the area and simply by substituting the value, you will get the resistivity. Then what about the conductivity? Conductivity kappa is nothing but the reciprocal of resistivity. So once you get this resistivity value, simply by taking the reciprocal of that resistivity, you can find out the conductivity. And what about the molar conductivity? Molar conductivity lambda m is equal to, once you get this conductivity value, that is kappa, the conductivity into 1000 divided by molarity, right? This molarity is given in the question 0.05. So, you can easily find out by substituting the values. Okay, you can do it by your own and you can put the answers in the comment box. Now, we are moving on to the very important section. Okay, that is the variation in conductance, conductivity, molar conductivity and equivalent conductivity with the concentration or dilution. So we want to find out whenever you are diluting or whenever you are changing the concentration. That's what dilution, right? So whenever you are diluting, whenever there is a change in the concentration, what happens? What will be the effect or what will be the variation in this conductance, molar conductance and equivalent conductance and conductivity and all. Okay. So we know that the solutions, we can categorize electrolytes or not solutions, the electrolytes. We can categorize the electrolytes as strong electrolyte and a weak electrolyte, right? What is the difference between these two? Strong electrolyte, it will be undergoing almost complete ionization, right? It will be giving the maximum number of ions. Weak electrolyte means it will be undergoing only partial ionization. Only few number, limited number of ions will be produced by this, right? Now see, actually, when you are diluting the solution, when you are diluting or when you are changing the concentration of an electrolyte, the electrolytic conductance, okay, the conductance as well as the conductivity and molar conductivity, the equivalent conductivity and the molar conductivity and also the conductance of the solution of, sorry, again solution, conductance of the electrolyte will increases with dilution, whereas the specific conductivity of an electrolytic solution decreases with the dilution. See, why? when you dilute or when you decrease the concentration, sorry, when you diluting, when you are increasing the concentration, why? The electrolytic conductance is increasing. If you are taking an electrolytic solution, when you are diluting it, what happens? This electrolyte will be completely dissociating, right? As the number of the ions are increasing, as the number of ions increases, definitely the conductance of the solution will also increase, right? So when in the electrolyte, when you are diluting the solution, the more number of ions will be produced there. This increase in the ions, the number of ions will be responsible for the increase in the conductance with the dilution. Okay. So same way, the equivalent conductivity and the molar conductivity also increases. That I will explain to you once I explain this. Why the specific conductivity of an electrolytic solution decreases? Specific conductivity means within a specified volume, how many number of ions are there which will carrying out the electrolysis, or which will be the carrying out the conductance, not electrolysis, which will be carrying the conductance, right? So when you are diluting means what will happen? The number of ions per unit volume is decreasing, right? Corresponding to that volume, the number of ions will be lesser in number. That is the reason when you are diluting the solution, the specific conductivity of a particular volume of solution will be decreasing as the number of ions per volume is decreasing there, right? And what about this equivalent conductivity and molar conductivity? This equivalent conductivity is nothing but the product of the specific conductivity into volume, right? So here in the second line we have mentioned the specific conductivity is decreasing, but this decrease in the specific conductivity is compensated by the increase in the volume. That is the reason the electrolytic equivalent conductivity as well as the molar conductivity is increasing with dilution. Okay. Here, the decrease in the specific conductivity is compensated by the increase in the volume. Okay. So, when you dilute the electrolytic solution, what happens? The conductance is increasing because of the increase in the number of ions upon dilution, and the specific conductivity and the equivalent conductivity and molar conductivity is also increasing because the decrease in the specific conductivity is compensated by increase in the volume. As the volume increases, there will be an increase in the equivalent conductivity and molar conductivity, whereas the specific conductivity of an electrolytic solution decreases with the dilution because the number of ions is carrying, the number of charge carrying particles will be per liter will be decreasing upon dilution. Okay. So now let's see the variation in the molar conductivity with the concentration. We have to take a consideration of the strong electrolyte as well as a weak electrolyte. Okay. So let's take the example of two electrolytes, one strong electrolyte and a weak electrolyte. Okay. So for a strong electrolyte, okay, you are taking a strong electrolyte, okay, and we are diluting it, right? So once you are diluting, when the concentration is C, the equivalent conductivity will be lambda C equivalent, right? So when you are diluting it, for a number of dilution after the infinite dilution, though you will be getting an equivalent conductivity value that we are representing with the lambda naught, and this value is what we called limiting conductivity. That means the conductivity at a infinite dilution. Okay, that is the limiting conductivity. Okay, so here for strong electrolyte means it will be ionizing, it will be giving maximum number of ions, right? So definitely they will have a more electrolytic power. So what happens for the electrolyte when you are decreasing, when you are diluting the solution? That means you are increasing or decreasing, the changing the concentration. Okay, for so strong electrolyte, you should know one equation, that is lambda equivalent. Equivalent conductivity at a concentration C will be equal to the limiting molar conductivity, the limiting conductivity, or the limiting, I can write it as the limiting molar conductivity. Okay, the molar conductivity at concentration C will be equal to limiting molar conductivity minus A root C, where lambda mc is the molar conductivity at a concentration C, and lambda m0 is the limiting molar conductivity. That is nothing but the molar conductivity at a infinite dilution. And A will be constant and its value will be different for different electrolytes. And C is nothing but the concentration. C is nothing but the concentration. And this equation for strong electrolyte is called Debye Huckel equation. Okay. Now let's see how we can find out this lambda naught m, limiting molar conductivity for a strong electrolyte. Okay. Here, okay. Here I am plotting a graph. We can plot a graph of molar conductivity the y-axis. I am taking the value 20, 40, 60, 80, 100, 120, like this, 140, like that. Okay. And in the x-axis, I am taking the square root of concentration. Okay. That value will be 0 0.2, 0 0.4, 0 0.6. Okay. So, here, see, For a strong electrolyte, you can see that when you decrease the concentration, okay, that means you are diluting the solution. When you decrease the concentration, you will be getting a, when you are decreasing the concentration, you can clearly see from the graph that there is no large decrease or large change in the molar conductivity. See, you are decreasing the concentration from here, this concentration to, okay, you are decreasing the concentration from this to this, right? You are decreasing the concentration. See, there is no large differences in the molar conductivity, right? The molar conductivity, there is only a slow decrease, and you can see that here the graph is not linear, but when you decrease the concentration upon dilution, more dilution, you can clearly see the graph become linear, whereas here the concentration is more, it is non-linear. What may be the reason for that? In strong electrolyte, we know that already the maximum number of ions are formed there, right? But these these ions will have a strong interionic attraction there, which restrict these ions from the movement or from their motion, right? When you dilute this, when you dilute the strong electrolyte, what happens? This interionic attraction decreases and the ions can move more easily, more freely. That is why upon diluting, you can see a slight increase with a linear plot, with a slight increase in the molar conductivity. Okay, and here you are getting a straight line graph, right? And when you extrapolate this graph to the y-axis, you can see at 0 time. That means at infinite dilution, you will be getting the molar conductivity value, and this value is nothing but the limiting molar conductivity. So for strong electrolyte, this is the representation for a strong electrolyte, right? So for strong electrolyte, you will be getting a straight line with only a minimum changes in the minimum value differences in the molar conductivity. And when you extrapolate this graph to the y-axis, you will get the molar conductivity at infinite dilution. That is nothing but the limiting molar conductivity, right? That's about for the strong electrolyte. There you should know this graphical representation as well as the Debye-Huckel equation for strong electrolyte. Okay. Now see for weak electrolyte. For weak electrolyte, when you are decreasing the concentration, there will be only a very little difference in the molar conductivity, and when you decrease concentration, that is upon further dilution, you can see a big increase in the molar conductivity, and it will be going like this. Okay, so initially when you decrease the concentration, there was not enough change in the molar conductance, but on further dilution, that means when you decrease the concentration, what happens? There is a sharp increase in the molar conductivity. What may be the reason for that? That's weak electrolyte. This is what we are representing for the weak electrolyte, right? This weak electrolyte will give only minimum number of ions, right? So upon diluting, what happens? Upon diluting the electrolytic solution, more ions are producing there. This increase in the number of ions is responsible for this sharp increase in the molar conductance upon infinite dilution of the weak electrolyte solution. Got it? So, see, here for weak electrolyte, the graph will be going like this. Can we extrapolate this graph to the y-axis? It's not possible, right? So, how can we find out the limiting molar conductivity for weak electrolyte? So, for weak electrolyte, to find out the limiting molar conductivity, there was a new method, that is the Colroche's law. Okay, so before that, I think this graphical representation for the molar conductivity versus concentration, root of square root of concentration for strong electrolyte as well as weak electrolyte is clear for you. Now we can go for the and this Debye-Huckel equation. It's also very important one. Now let's see the very important term, that is the Colroche's law. Okay, the Colroche's law states that this is a very important one. It states that the limiting molar conductivity of an electrolyte, that is the molar conductivity at infinite dilution. That's what the limiting molar conductivity, right? That is the lambda not m. Okay. The limiting molar conductivity of an electrolyte is the sum of the limiting ionic conductivities of the cation and anion, each multiplied with the number of ions present in one formula unit of the electrolyte. I will simplify it. See, if you have an electrolyte AXBY, okay, if this is your electrolyte, according to Colroche's law, the limiting molar conductivity of this AX By is nothing but the sum of the ionic conductivity. This AXBY will be dissociating to A plus and B minus ions, right? So this A with the number of atoms, its given number of ions as it's given by X rho. According to this Colroche's law, the limiting molar conductivity of AXBY is nothing but X into limiting molar conductivity of A minus ion, sorry, A plus ion plus Y into the limiting molar conductivity of B minus ion. The limiting molar conductivity of the electrolyte is the sum of the ionic conductivity of cation and anion, each multiplied with the number of ions present in the one formula unit. This is what the formula unit. In that the number of ions is, we have to multiply ionic conductivity with that number of ions in the electrolyte. Okay, we can take one example. See, what will be the limiting molar conductivity of sodium chloride? Sodium chloride will be dissociating to give Na plus and Cl minus, right? So then it will be limiting molar conductivity of Na plus the limiting molar conductivity of Cl minus ion. What will be the value for barium chloride? The limiting molar conductivity of BaCl2. The BaCl2 will be dissociating as Ba2 plus 2Cl minus, right? Then it will be the limiting molar conductivity of barium plus 2 into limiting molar conductivity of Cl minus. If so, just tell me what will be for aluminium sulfate, Al2SO4 thrice. What will be the limiting molar conductivity? Sorry. Limiting molar conductivity of Al2SO4 thrice. It will be 2 into the limiting molar conductivity of Al3 plus 3 into limiting molar conductivity of SO4 2 minus, right? This is what the Colrosius law. For weak electrolyte, we can find out the limiting molar conductivity by adding the sum of the limiting ionic conductivity with the multiplied, each the cation and anion is multiplied with the number of ions present in it. That is what the Colrosius law. Now let's see the applications of Colrosius law. The first application is the calculation of the molar conductivity at infinite dilution for weak electrolyte. The same thing what we discussed for Colrosius law. If you know the ionic concentration, we can find out the limiting molar conductivity. If you don't know the ionic concentration also, see, if you want to find out the limiting molar conductivity of acetic acid, okay, CH3COOH we are taking. Okay, if you want to find out this value, this will be equal to the limiting molar conductivity of acetate ion plus the limiting molar conductivity of H plus ions, right? So instead of this, if you know the limiting molar conductivity of CH3COOK, potassium acetate, and the limiting molar conductivity of potassium chloride and limiting molar conductivity of HCl, we can easily find out the limiting molar conductivity of CH3COOH will be equal to, from this will be dissociating to give the CH3COO minus plus K plus, right? This will be giving K plus Cl minus. This will be giving H plus Cl minus. So what you need? You need this one and this one, right? So what you can do? You can just simply add this two, and from that you have to minus this chlorine and potassium, right? So for that what we can write? This is equal to the limiting molar conductivity of CH3COOK plus the limiting molar conductivity of HCl minus, so yeah, added this 2, right? And we know not needed this Kl and potassium that we have to subtract. That will be equal to limiting molar conductivity of KCl. So if you know these values of these three electrolytes, you can find out that of the acetic acid. That's what the first application, calculation of the molar conductivity at infinite dilution for weak electrolytes. Okay, now let's see one question. Find out the molar conductivity of an aqueous solution of barium chloride at infinite dilution when ionic conductance of barium and chloride ions is, it's a direct question, right? Barium chloride, you know, barium chloride, Ba2 plus plus 2Cl minus, right? And the ionic conductances of barium and chloride is given. So what you want to find out? The limiting molar conductivity of BaCl2, right? It's nothing but the sum of the limiting molar conductivity which is given. Okay, the ionic conductivity is given. The limiting ionic conductivity of Ba2 plus plus 2 into the ionic conductivity of Cl minus. Okay. Then simply by substituting the value, the barium value, it is given 127.30 plus 2 into 76.34. By simply doing the values, and your final answer will be in Siemens centimeter square mole inverse. You will get the value. Okay. That's a very simple application. Okay. Same way. See here. You want to find out the molar conductivities at infinite dilutions of barium hydroxide, barium chloride and ammonium chloride are given. Okay, that is 517.6, 240.6 and 129.8 ohm inverse centimeter square mole inverse respectively. You want to find out the limiting molar conductivity of ammonium hydroxide solution. See here, first you write the equation for limiting molar conductivity of ammonium hydroxide will be equal to the ionic conductivity of NH4 plus plus the ionic conductivity of OH minus. And in the question what it is given, the limiting molar conductivity of BaOH twice, that's equal to the ionic conductivity of Ba2 plus plus 2 into the limiting molar ionic conductivity of OH minus, right? And the next one is barium chloride. Limiting molar conductivity of barium chloride will be equal to Ba2 plus plus 2 into the ionic conductivity of chloride ion. What about the limiting molar conductivity of NH4Cl will be equal to NH4 plus Cl minus, right? So from this three given data, how can you find out the value? Okay, you want to find out for NH4OH, right? So you want this one, okay, plus, but here 2 into OH minus values is there. So you have to divide this first equation with the 2. Then you will get the OH value, right? Then NH4OH. Then what you required, NH4OH you got. Here one chlorine was there that you want to remove. For that also you want to divide this equation with the 2 because there are also 2 chlorine is there, right? So divide this value with the chlorine. So now see NH4, this OH minus divided by 2 means it will be giving the OH value. So you have to divide this whole value. What is the value limiting molar conductivity of OH minus by 2? And this value also you have to divide by 2 because 2 chloride ions are there, right? Then you will get NH4OH value. See, first one ammonium chloride. For ammonium chloride, the value is 129.8 plus for barium hydroxide, 2 hydroxyl ions are there. So you have to multiply by 2. So barium hydroxide value is 517.6 divided by 2 minus, what's the value for barium chloride? Barium chloride is 240.6 divided by 2. Okay, that will be the limiting molar conductivity of NH4OH. That's equal to 129 by 2 plus 2, 5, 258 divided by Okay. So what you will get here? 6 387 minus 120.3. So here you will be, everything is right? 517 for barium hydroxide. Have taken barium hydroxide, but this is not okay. NH4Cl, NH4OH plus 1 by 2 minus 240.6, right? 2 2s are 4, 5, 8, 2 2s are 4, 1, 2 2s are 4, 0.3. So simply by doing this calculation, you will get the value for the limiting molar conductivity of ammonium hydroxide. Okay. Next application. So the first application is the calculation of molar conductivity at infinite dilution for weak electrolyte. The second application is the calculation of degree of dissociation. Degree of dissociation is nothing but the alpha. Okay. The degree of dissociation is nothing but the alpha. Okay. So here what we got is, the degree of dissociation alpha will be equal to the molar conductivity at concentration C divided by the limiting molar conductivity. If the molar conductivity at a particular concentration is given, and if you know the limiting molar conductivity, you can easily find out the degree of dissociation alpha. Okay. So see, they calculate the degree of dissociation of acetic acid. If its molar conductivity, it is given as the 39.05. Given ionic conductivity. Ionic conductivity is given here for acetate ion as well as for the H plus ions. That is 349.6 and 40.9. So, you have to find out the limiting molar conductivity of acetic acid as adding the sum of the limiting ionic conductivity of CH3, COO minus plus H plus ions. Okay. Once you get this value, you can find out the degree of dissociation as the molar concentration, molar conductivity at a concentration C, which is given in the question as 39.05 divided by the limiting molar conductivity. That value you are finding out here by adding ionic conductivity. Okay. And the third application is the calculation of dissociation constant of a weak electrolyte. Okay. So here for the dissociation constant, K will be equal to C into alpha square divided by 1 minus alpha. Okay. The dissociation constant for weak acid electrolyte is K is equal to C into alpha square by 1 minus alpha. Okay. So we have find out the, how we can find out the degree of dissociation, right? Once you get the degree of dissociation, you can find out the dissociation constant K or Kc using the equation C alpha square divided by 1 minus alpha. Here is a one numerical based on that. That is at 291 Kelvin, the molar conductivity at infinite dilution of ammonium chloride, NaOH and NaCl are 129.8, 217.4 and 108.9 Siemens centimeter square respectively. If the molar conductivity of a centinormal solution means 1 by 100th of the original concentration of ammonium hydroxide is 9.33 Siemens centimeter square. What is the percentage dissociation of ammonium hydroxide at this dilution? Also, you want to find out the dissociation constant of ammonium hydroxide. So, for that, First you have to find out the limiting molar conductivity of ammonium hydroxide from the given values of ammonium chloride, NaOH and NaCl. So, from the first method itself, you can find out the limiting molar conductivity, and the molar conductivity at a 1 by 100th concentration. That means the lambda M value of NH4OH is given as 9.33, right? From this value, you can easily find out the lambda value by the NH4OH divided by the limiting molar conductivity. This one you can easily find out from the ammonium chloride, NaOH and NaCl value, right? So once you get this value, you will get the percentage dissociation, that is the lambda value, right? So then how will you find out the dissociation constant? It is nothing but the C alpha square by 1 minus alpha. Once you get this alpha value, you have to use that value here, and C is nothing but 1 by 10 means 0.01 into what the value of alpha you are getting divided by 1 minus alpha. Try to do this numerical and give your answer in the comment box. And your final application of Kohlrausch's law is the calculation of solubility of sparingly soluble salt. Okay, we know that some soluble substances, salts like salts are sparingly soluble. That means they will not be get completely solubilized. Only a small portion will be solubilized, right? So for calculating the solubility of such sparingly soluble salt, we can use Kohlrausch's law. There, the limiting molar conductivity lambda m value will be equal to the kappa into the specific conductivity into 1000 divided by molarity, right? That we can rewrite it as K into 1000 divided by solubility. So the solubility will be equal to what? The specific conductivity kappa into 1000 divided by the limiting molar conductivity. Okay, so with this we can find out the solubility of sparingly soluble salt, because sparingly soluble salt we will treat it as the weak electrolyte because they are dissolving only a little amount, right? So we can consider it as the weak one or as a diluted one, right? So that's for the applications of Kohlrausch's law. The Kohlrausch's law we can use. The main applications are calculation of the molar conductivity at infinite dilution of weak electrolyte. Second one is the calculation of degree of dissociation. Third one is the calculation of dissociation constant. And the final application is calculation of solubility of a sparingly soluble salt. Okay, I hope this Kohlrausch's law is clear for you. With this, I am winding up today's session and I will be coming with the last part of this electrochemistry chapter, that is the battery and corrosion, in the next live session. But until then, thank you all, and don't forget to stay tuned with Goscore Learning tomorrow for your physics class by Nandini ma'am. Thank you all.